Imagine a power grid running entirely on sun and wind, completely clean. There's just one problem. The sun sets, the wind drops, and the lights can't go out. So how do we make clean energy reliable? The answer is hiding kilometers beneath our feet. In this video, we're going on a journey from the deep physics of storing carbon and hydrogen underground, all the way to the machine learning that's making it work. Let's dig in. Here's the core problem with renewables. They're clean, but they don't show up on schedule. Solar peaks at midday, but our demand peaks in the evening, when everyone gets home. You can see it in this chart. The orange supply curve and the blue demand curve just don't line up. That midday gap is the famous duck curve. And it's not just daily. There's a seasonal mismatch too, summer sun versus winter heating. The result? We waste surplus power in the afternoon and fall short at night. So the obvious fix is storage. Save the extra energy for later. And batteries are fantastic, for hours. They smooth out seconds and shift power from afternoon to evening. Pumped hydro can stretch that to days. But look at the right-hand side of this slide. To balance summer against winter, you need to store energy for weeks or even months. That's a completely different scale, and it's where batteries simply can't compete. For seasonal storage, we have to go underground, into porous rock, because nothing else is big enough. So the obvious fix is storage. Save the extra energy for later. And batteries are fantastic, for hours. They smooth out seconds and shift power from afternoon to evening. Pumped hydro can stretch that to days. But look at the right-hand side of this slide. To balance summer against winter, you need to store energy for weeks or even months. That's a completely different scale, and it's where batteries simply can't compete. For seasonal storage, we have to go underground, into porous rock, because nothing else is big enough. Let's follow the carbon's journey. Step 1. Capture. We separate CO2 from flue gas, or even pull it straight from the air. Step 2. Transport. We compress it into a dense, supercritical fluid and move it by pipeline. Step 3. We can utilize it, recycling the carbon into fuels, materials, or concrete. And Step 4. Storage. Injecting it deep into saline aquifers or old depleted oil and gas fields. The net effect? Carbon that would have warmed the atmosphere is locked into rock for thousands of years. Hydrogen works as a loop. Start with surplus power. That's solar and wind we'd otherwise throw away. Run it through electrolysis to split water into green hydrogen with zero carbon. Then store that hydrogen in salt caverns or porous rock for weeks or months. And when demand spikes and the grid runs short, we recover it, burning it in turbines or running it through fuel cells. Store energy as a chemical bond when it's abundant, release it when it's scarce. Season after season. Here's how it all fits together. On the left, variable solar and wind feed into the grid, whose only job is to keep supply and demand perfectly balanced. The trouble is that balance keeps breaking. That's where our two technologies plug in. CCUS acts as a sink, absorbing CO2 from the industries we can't easily clean up. And UHS acts as a buffer, banking surplus energy and giving it back later. Notice that both live underground, which means everything comes down to the physics of fluids moving through rock. So where does it actually go? 3 kinds of underground store. Saline aquifers, deep porous rock full of salty brine with enormous capacity. These are the workhorse for CO2. Depleted reservoirs, old oil and gas fields that already have proven seals and decades of data. And salt caverns, engineered voids that are tight and flexible, perfect for hydrogen. The key to all of them is what's shown at the bottom. A caprock seal, an impermeable barrier that traps the buoyant fluid in the porous reservoir below. Now for part 1, the physics. Because the moment you inject a buoyant fluid into rock kilometers down, forces start fighting it out. How it flows, how heat and pressure shape it, how it stresses the rock, and how it chemically reacts. Get these right and storage is safe and permanent. Get them wrong and the fluid escapes. Let's look at each one. First, multi-phase flow. When you inject CO2 or hydrogen, you suddenly have 2 fluids competing for the same pore space. Your injected gas and the brine that's already there. How fast each one moves is governed by Darcy's law. Flow rate equals permeability times mobility times the pressure gradient. The crucial term is relative permeability, shown on the right. As gas fills the pores, the brine's ability to flow collapses and the gas takes over. And because hydrogen is about 10 times thinner than brine, it slips through far more easily. Zoom into a single pore and surface tension takes over. Capillary forces literally pin fluid in place. Over time, for trapping mechanisms make storage progressively more secure. First, structural trapping. The buoyant fluid rises until the caprock dome stops it. Fast, but it relies on the seal. Then residual trapping. Blobs snap off and get stuck in tiny pore throats. Then solubility trapping. The fluid dissolves into brine, which sinks, very stable. And finally mineral trapping. The carbon reacts to form solid rock. Each step locks it in tighter. Why do we keep saying dense fluid instead of gas? Thermodynamics. As you go deeper, both pressure and temperature climb. Push CO2 past its critical point, about 31 degrees Celsius and 74 bar, and it becomes supercritical, as dense as a liquid, but flowing like a gas. You can see the supercritical region on this phase diagram. That density is everything. It's what lets us pack huge amounts of CO2 into a compact underground space. And it's why we need a depth of roughly 800 meters or more. Here's the catch. Injecting fluid raises the pressure underground, and that pressure stresses the rock. Push too hard, and 4 things can go wrong. You can crack the caprock seal, so you must always stay below its fracture pressure. You can reactivate a fault, unclamping it, and risking leakage or small tremors. You can even lift the ground at the surface, something we can actually measure from satellites. And all of it is coupled. The flow and the rock deformation constantly feed back on each other. Geomechanics sets the safe operating envelope. Then there's chemistry, because the fluid can change the rock itself. CO2 dissolved in brine forms a weak acid. That acid slowly dissolves some minerals and precipitates others, eventually turning carbon into solid carbonate stone, the most permanent fate of all. But as those reactions proceed, they reshape the pore network, which changes the flow. And that's the real challenge of the subsurface. Flow, heat, mechanics, and chemistry aren't separate problems. They're one tightly coupled system, what engineers call THMC coupling. Hydrogen deserves its own slide, because it plays by its own rules. It's the smallest, lightest molecule we store underground, and that changes everything. Very low viscosity means it fingers unpredictably through brine. Very low density makes it strongly buoyant. It races toward the seal. Its high diffusivity lets it seep through tight materials. Underground microbes can literally eat it. It gets cycled in and out constantly, fatiguing the rock and wells. And you need cushion gas, a permanent base volume, just to maintain working pressure. Here's the beautiful part. Every single effect we've covered reduces to a handful of conservation laws. Mass conservation says fluid in minus fluid out equals the change in what's stored. Darcy's law says pressure and gravity drive the flow. And the energy equation tracks heat and chemical species carried along with the fluid. These are coupled partial differential equations, the complete mathematical description of our problem. The only thing left is to solve them, everywhere, for decades of injection. And that is a serious computational mountain. So how do we solve them? With a reservoir simulator. First, we grid the rock, slicing the reservoir into millions of little cells, each with its own properties. Then we discretize the equations, turning calculus into algebra the computer can crunch cell by cell. Then we solve each time step, marching forward in time while balancing flow and pressure across the whole grid. And out comes a prediction, where the plume spreads, how pressure builds, and how secure the storage stays over decades. These simulators are the industry workhorse, physically faithful, but, as we'll see, painfully slow. And that's the bottleneck. A single high-fidelity simulation can run for hours, sometimes days. That's fine for one answer. But good decisions don't need one run, they need thousands. Why? Because the rock underground is never fully known, so we have to explore many scenarios and quantify the uncertainty. Look at this chart. 1,000 runs on a full physics simulator could take months. The same 1,000 runs through a machine learning surrogate? A few hours. That gap is exactly why physics alone isn't enough anymore. There's one more reason this is so hard. Scale. The physics that matters in a single pore, micrometers across, has to inform a model that covers an entire sedimentary basin, hundreds of kilometers wide. That's 9 orders of magnitude, from pore to core sample, to well, to reservoir, to basin. No single simulation can resolve all of it at once. And that, the combination of crushing cost and impossible scale, is exactly where machine learning earns its place. Welcome to Part 2, Machine Learning. And I want to be crystal clear about one thing up front. ML is not here to replace the physics. It's here to accelerate it, to fill the gaps where our data is thin, and to turn those painfully slow simulators into instant answers. We'll cover 5 big uses: surrogates, physics-informed networks, inversion, monitoring, and optimization. Let's go. Machine learning runs on data, and the subsurface is genuinely data-hungry. Here's the hard truth. Every model is only as good as what it learns from, and for storage sites the data is sparse, expensive, and indirect. We're trying to infer an entire 3-dimensional volume from a few scattered measurements. Seismic surveys that image the moving plume, well logs down each borehole, precious core samples for ground truth, live pressure and rate data, ongoing monitoring, and even millimeter-scale surface deformation maps from satellites. The single biggest win is the surrogate model. The idea is elegant. Run the full physics simulator just a few hundred times, then train a neural network on those results until it learns the input-to-output mapping. After that, the network predicts brand new scenarios in milliseconds instead of hours. We're talking speed-ups of 100 to 10,000 times. Suddenly, you can do real-time what-if analysis. And, crucially, you're now fast enough to search through thousands of possible designs. This one trick unlocks almost everything that follows. But pure data models have a weakness. They can confidently break the laws of physics. Enter the physics-informed neural network, or PINN. Instead of just fitting data, a PINN is penalized whenever it violates the governing equations. The PDE residual literally becomes part of its loss function. So the total loss combines 2 parts, a data loss that fits the measurements and a physics loss that forces the equations to hold. The payoff? It needs less data. It stays physically consistent even where data is missing, and it's brilliant at solving inverse problems. Speaking of inverse problems, this is history matching, and it's the heart of it. We can't measure the rock directly, so we infer it. We guess the properties, permeability, porosity, fault seals. We predict the response using our fast surrogate. We compare that prediction to the real sensor data, and then we update our guess and repeat. The clever part is that machine learning steers each new guess intelligently instead of blindly. We iterate until the model reproduces the past, and once it can, we can finally trust its forecasts. Once injection starts, the whole job becomes assurance, proving the fluid stays exactly where it should. And ML is a tireless watchman. It can track the plume automatically, turning repeated time-lapse seismic into a moving map. It can detect anomalies, spotting pressure or signal patterns that just don't fit the model. And it provides leakage assurance, an early warning if fluid starts migrating toward the seal or a fault. Look at the chart. The measured signal quietly diverges from what we expected, and the model flags it long before a human would. Remember how surrogates made everything fast? Here's the payoff. With an instant model in hand, we can search enormous design spaces to find the best possible way to operate. Where exactly should we drill the wells for maximum storage and safety? How fast can we inject without fracturing the seal? For hydrogen, when do we store versus withdraw across the seasons? And how do we trade off capacity, integrity, and cost? Finding the optimal answer to questions like these is simply impossible with slow simulators alone. And here's the most honest thing machine learning gives us: error bars. Because the subsurface is never fully known, a single confident prediction is actually misleading. So instead we run huge ensembles, thousands of plausible Earth models, cheaply, thanks to our surrogates. Then we report a range. Not, the plume goes exactly here, but here's the probability it goes here, shown as P10, P50, and P90. Look at the fan of forecasts widening over time. The spread isn't a bug, the spread is the message. Now, a reality check, because ML is powerful, but it is not magic. Data is scarce, few sites, few wells. Models can fail to generalize. What works in one field may flop in the next. They can be hard to interpret, and a black box is hard to certify. Pure data models can break physical laws. We're asking for thousand-year forecasts from just years of data, and regulators rightly demand explainable, auditable models. These are the open problems researchers are working on right now, and the reason physics still matters. So where is all of this heading? Toward digital twins, live, self-updating models of each storage site, fed continuously by streaming data. Toward foundation models, large, pre-trained geoscience models you fine-tune for your specific site. Toward hybrid physics ML systems becoming the default, with simulators and networks working as a single engine. And toward basin-scale planning, coordinating many sites and their shared pressure across a whole region. The through line is simple. Physics gives us trust, machine learning gives us speed, and the renewable grid needs both. So let's bring it home. Renewables make clean power, but it's the subsurface that makes it reliable. CCUS and underground hydrogen storage let US bank carbon and energy kilometers below ground. The physics, flow, thermodynamics, mechanics, and chemistry sets the rules. And machine learning is what makes it fast, data efficient, and ready for real decisions. Put them together and you get a grid that's both clean and dependable. If this video connected the dots for you, hit like, subscribe for more deep dives, and share it with someone who'd find it fascinating. Thanks for watching.